In this segment, we focus on a group of lipids known as triglycerides, which are also referred to as triacylglycerol and triacylglyceride. We'll get into the spelling of that a little bit later. Triglycerides are very common lipids. In fact, they are the most common component of fats, referring to body fat and also referring to fat within the food that we eat. They're also prevalent within skin oils, and they're essential within blood, primarily for serving the purpose of transporting glucose from the liver to other locations within the body. In this video, we will learn about the structure of a triglyceride molecule, and we'll also learn about how those molecules are formed biologically within the body, what relationship they share to fatty acids, and how triglycerides are ultimately broken down and converted back into other molecules. Let's go ahead and take a closer look. Triglycerides, also known as triacylglycerols and triacylglycerides, have the common structure theme that we see here. This is represented by a total of 3 ester groups here, here, and here. Those ester groups have a long chain bonded to them, here called R1, here called R2, and here called R3. Those could be either saturated or unsaturated chains. So these are our alkyl chains, generally very long, because as we will learn in a moment when we look at the reaction that creates these molecules are created from fatty acids, where the R group on the fatty acid becomes the R group here, and fatty acids have notoriously long R group alkyl chains. And this can be unsaturated, meaning there's at least one or more carbon-carbon double bonds, or they can be fully saturated, which means they've maxed out the number of hydrogens that can be there relative to the number of carbons, meaning that there have to be exclusively carbon-carbon single bonds there. In addition to having an ester group, what the molecules also have in common is you will notice that there's a 3-carbon chain over here that I'm putting vertically, and each of those 3 carbons have an oxygen bonded to it. So here, here, and here, with those 3 carbons being linked into a chain. This particular structural component is derived from a molecule known as glycerol. The reason why I say it's derived from glycerol is glycerol, we will see, is a reactant that is required for the synthesis of triglyceride. Glycerol is a 3-carbon triol. By triol, T-R-I, referring to 3, OL referring to alcohol, we're referring to a molecule that has 3 alcohol groups. And in fact, the 3-carbon chain of glycerol has an oxygen atom, a hydroxy group, on each of the 3 carbons. So the formula for that molecule is CH2OH, 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 allowing each of those 3 carbons to have a complete octet, and each of those carbons has a hydroxy group. Now, the reason why we call this a triglyceride is the term glyceride is derived from the precursor glycerol, the alcohol form of the molecule, and tri is referring to the fact that all 3 of those alcohol groups have bonded to form an ester functional group. Triacylglycerol, the glycerol part of that name, is referring to the parent compound of these molecules, meaning the precursor that reacted in order to give the product that we see here. The triacyl part of that refers to the structure of a so-called acyl group. An acyl group refers to a carbonyl that is directly bonded to an R group, in this case R1, R2, or R3, hence 3 acyl groups. In this name, triacylglyceride, we apply that term the same way, referring to the 3 carbonyl groups bonded to the 3 R groups, and then the term glyceride is referring to the fact that the molecule is derived from the 3-carbon alcohol glycerol. How are triglyceride molecules, such as the product shown here, formed? Well, we start from glycerol, a biological molecule, it reacts with 3 fatty acids produced either by the body or consumed dietarily. The linkage of those 3 fatty acids to each of the 3 alcohol groups of glycerol yields the triglyceride product in a reaction that is reversible. Enzymes catalyze these reactions within the body to interconvert between triglycerides and fatty acids, creating an equilibrium back and forth in this reversible reaction. Within this reaction, as we dissect it, what we see is that one of the alcohol groups reacts with one of the fatty acids to give an ester product up here. The second alcohol group reacts with the second fatty acid to give the product here. And the third reacts with the alcohol group here of the glycerol reacting with the fatty acid to give the ester group here of the product. So really what this represents is 3 Fischer esterification reactions. And we're able to do 3 Fischer esterifications because we have a single alcohol molecule, glycerol, that has 3 alcohol functional groups. And so each of those can react with a separate fatty acid molecule. These fatty acid molecules can be either saturated or unsaturated. And I really should say saturated and or unsaturated, because in a particular triglyceride molecule, the 3 fatty acids that form bonds here do not have to be identical to one another. In other words, they can be 3 different fatty acids, or alternatively, they can be the same. If the 3 are identical, we refer to the resulting triglyceride as a homotriglyceride. Homo meaning same. And as you might predict if you're thinking ahead here, if the fatty acids differ from one another, then we refer to it as a heterotriglyceride instead. Now, in these reactions, water will be a product of the reaction because just like in a typical Fischer esterification reaction, what we do in the reaction is we replace the OH group of our fatty acid with the O-alkyl group from our alcohol, which in this case is referring to replacing the OH group here of our fatty acid with the O-alkyl group of our glycerol molecule. Doing that at each of the 3 positions, replacing the alcohol group, or I should say hydroxy group of our fatty acid with the O-alkyl group from our alcohol there in the middle, and also here on the top. Hydroxy group gets replaced with the O-alkyl group from our alcohol to give us ultimately the ester bonds in the product. And it's an important and great idea when you're drawing these to always be on the lookout to make sure that the ester functional group is in place. And you would be correct if, as you are looking through these materials, you're getting the idea that the ester functional group is very vitally important, as is the Fischer esterification reaction, because we saw the Fischer esterification reaction also occurring in the synthesis of waxes. And now here it goes again with the production of triglycerides. So within the body, as the body stimulates the production of additional triglycerides, the production of the enzyme that catalyzes this reaction would be upregulated. And then to allow the reaction to go in the other direction, enzymes would catalyze that process as well to favor going in the reverse direction. Now let's take what we've learned and apply it toward a problem. I encourage you to hit the pause button, try to do this on your own, and then hit the play button to go forward. We are asked here to provide the homotriglyceride structure that results from reacting naturally occurring 16:1N4 fatty acids with glycerol. There's a lot to unpack here. Let's go ahead and get started on that. When we refer to a 16:1N-4 fatty acid, what that's referring to is that there are 16 carbon atoms in total. There is 1 carbon-carbon double bond, and that carbon-carbon double bond starts at carbon number 4 of the chain, numbering with the end of the alkyl group, the methyl group of the alkyl group being carbon number 1 of the chain. We'll react 3 of those with glycerol to give a so-called homotriglyceride structure. The homo part there of the name refers to the fact that all 3 fatty acids are identical. If we were using 3 different fatty acids, we'd be creating a heterotriglyceride, and those 3 different fatty acids could be shown in any order within the product. Okay, so taking a look at our reactants, I'm going to go ahead and draw out the structure of glycerol. I like to draw that vertically for illustration purposes. It helps orient the final product, but certainly you could draw this out horizontally as well. There's nothing wrong with that, but I like this vertical orientation so that I can see visually how the reaction is occurring. So this is my glycerol reactant, a 3-carbon triol with an alcohol group on each of the 3 carbons. Then I'm going to bring in my 3 16:1N4 fatty acids. Those would be required to have a carboxylic acid group since they are fatty acids. And then in the structure, 16 carbon atoms in total. That includes the carbonyl carbon. And we need to have a carbon-carbon double bond at position number 4 of the chain. So I'm going to plug in here some CH2 groups. I'm going to leave this as CH2, and then I'm going to leave a blank space here so I can later fill in the number of those in my condensed structural formula. I'm going to fill in my carbon-carbon double bond right there, and I'm going to make sure that that ends up at position number 4 relative to the end of the carbon chain. So I plug in my hydrogen here, and then I continue my carbon chain to do CH2, CH2, CH3. And numbering, remember, from the end, starting with the methyl group. This is opposite how we would number for IUPAC nomenclature, but that's how we do it for fatty acids. N4 refers to the fact that starting at carbon 4 is where we have our carbon-carbon double bond. And then since we need 16 carbon atoms in total, in other words, that carbonyl carbon would be number 16 in the chain, since I've shown 5 carbons here explicitly, and we've also shown 1 carbon explicitly as the carbonyl, that's 6 in total. So therefore, I would need a grand total of 10 of those CH2 groups. Now, for clarity purposes, I've gone ahead and erased the numbering that I used to identify the carbon atoms of the chain so that I don't mistake those numbers for the number 10 here that I have referring to how many CH2 groups we have. I also want to fill in correctly the cis configuration of this. To do that, I need to show that the carbon chain forms this bowl shape where relative to this carbon, we're going upward with the rest of the parent chain, and relative to this carbon, we're also going upward here. And now we've drawn our structure of our naturally occurring meaning it's cis, 16:1, referring to the alkene group, and 16 carbons in total, N4, referring to where the alkene group is located. And now we're ready to create the triglyceride product. I'm going to redraw my glycerol molecule like it was from the beginning, except I'm going to leave off the hydrogen atom from each of my alcohol groups, because when we do a Fischer esterification reaction, what we do is take the O alkyl part of our alcohol. In this case, there will be 3 O alkyl parts here, here, and here of our glycerol, and that is what's going to link to the carbonyl group and the chain. That is what we refer to as our R group of our starting material, our acyl groups there. So now what I do is link the oxygen atom from each of my glycerol hydroxy groups to the carbonyl that was derived from our starting structure. So that carbonyl that I've highlighted in blue, and then the R group comes along with it here. So I would draw out each of these R groups here as well. So I'll go ahead and give that a go here. And I'll speed this along to show you how this goes. So now, in the final product, what we have done is copied down each of the 3 R groups from our fatty acid. Along this chain, I have been careful to keep in mind the stereochemistry at the alkene group, showing that it is cis in each of these cases, or bowl-shaped, as I am putting it. At every other location along the chain where we have a fully saturated carbon chain of single bonds, it doesn't matter how we orient that chain because that chain is subject to free rotation at those points. It's just there at the alkene group that the chain is locked into place in the cis configuration. To double check our work, we should have created in a triglyceride by definition a molecule that has 3 ester functional groups. And indeed, in looking at this structure, we have successfully created a molecule that has 3 ester groups. Those ester groups are here, here, and here, derived from each of the 3 hydroxy groups of the alcohol part of the molecule that we showed in red, and then the part that's derived from the fatty acid we showed in blue here to create this homotriglyceride product. Now, with this information in mind, if you are given some example fatty acids or given characteristics of those, you should be able to draw triglyceride products that will result from this Fischer esterification type reaction. Likewise, if you are given a triglyceride, you should be able to indicate what the structures would be of the fatty acids that were used to create that. Since this reaction is reversible, we can go back in this reverse direction. You should be able to take the structure of a triglyceride and tell me what fatty acids would that correspond back to. In other words, what would the structures be here, here, and here if we broke those away and reversing the reaction to create fatty acid products in the reverse reaction scenario, which happens metabolically as the body converts fatty acids into triglycerides and vice versa to meet whatever the body's needs are at that particular moment.